Here today to present Uncovering the Secrets of Nanotechnology. Please join me in welcoming to the stage Jamie Gallagher. Thank you.
Thank you. Thank you. Hello. It's so awkward standing at the side listening to yourself be introduced. I'll kind of introduce myself a little bit as well, but with less achievements than just kind of me as a human to start off with, if that's okay. Thank you for joining me as well. I decided to kind of introduce myself picking 3 pictures that I felt summed me up as a kind of person. If I start off in the middle here, that's maybe the core of what we'll be talking about today. That's me during my PhD, and you see I wore a onesie for most of it because I worked with nanotechnology. So that these suits are made of a special material that avoid fibers getting onto my work. So working on things so incredibly small that fiber, hair, skin falling from me would potentially destroy the things that I worked on. I also spend a lot of time up on stage. It's me at one of the science festivals setting a small fire, sharing my love of science as well, because I love science and I love talking, so talking about science is just fantastic to me. And the third image, does anyone recognize the person? We're off to a bad start, Leicester. Gates McFadden? Still nothing. Dr. Crusher from Star Trek. What does Dr. Crusher from Star Trek have to do with my slide? Yes, few nodding recognition. I'm a massive sci-fi fan. I love Star Trek, I love fantasy, and that represents part of my character that I infuse through my communication. The other reason that photo is there is because of the pose that we're in. So we're in a dance pose, as well as being a fantastic actor. Gates McFadden is a choreographer. She choreographed film Labyrinth. And as well as being a scientist and a science communicator, I'm also a dancer, so I teach people salsa. That's not the plan today. If all goes horribly wrong, up on your feet and find a partner. But today is not about me, it's about nanotechnology, something that I deeply love and I'm fascinated by. One of the things that's interesting is the word nano and nanotechnology have filtered through into everyday society. Not only the uses, but also the terminology. But there's a few problems. If you Google the word nano, this is what you get. Now that's not nano. That's not even nearly nano. That is 3 billion nanometers across the nano car. Even our electrical devices, so there was the iPod Nano, which was launched, again, not nano, and it got even less nano when it moved on to a newer generation. Nano has become a word that is associated with technology and advancement and great electrical devices, but it's also allowed a misunderstanding to creep in as to what nano actually is and what it's used for. So, to start off, I just wanted to kind of define, when I'm talking about nanotechnology, what am I meaning? And I think about the best definition that we have is the European Commission's definition. It's rather long-winded, but nanotechnology is the understanding and control of matter at dimensions between approximately 1 and 100 nanometers, where unique phenomena enable novel applications. Encompassing nanoscale science, engineering, and technology, nanotechnology involves imaging, measuring, modeling, and manipulating matter at this length scale. To break that down, what it's really saying, the important parts, understanding and control. So we're talking about something that we are able to use and control. Between 1 and 100 nanometers. Again, a very important definition. Sometimes when you see nano things reported in the media, they're much bigger than that scale. But we need to be under 100 nanometers if we're thinking about this as a nano application. Also, different behavior means different applications, this unique phenomena. When you get down below 100 nanometers, things behave in a slightly different way. Lots of different effects come into play, and it allows us to use those unique properties for the new applications. And the other section here is basically saying it involves lots of different subject areas. Physicists, chemists, biology, engineers, we're all interested in the area of nanotechnology. It is affecting every single area of science. But picturing it is something that is quite tricky. I like to think of just starting in our world. So here's something that you could measure on the decimeter scale, a football. You could pick it up, should be a rugby ball since we're here. You can pick it up, you can feel it, you can manipulate it, you can understand it. We get smaller, down another length scale, down to centimeter, something like dice, again, something you can pick up, you can feel, you can manipulate, and you can see detail on it. Not even near the nanometer yet. Once we get down to a kind of millimeter level, down around a fruit fly is about 2 or 3 millimeters across, we're getting to the level where our eyes are not really sufficient to see a lot of the detail on the fly, but we would be able to see it flying around. If we get smaller, down onto the micrometer level, if you feel your hair is really getting to the extent of our perception. We can see a single strand maybe, you can feel it maybe between your fingers, but we're still miles off that nanoscale. Jumping down several, down to a micrometer level, on a micrometer scale, things like red blood cells. Again, much, much bigger than the level that we're working at. We're almost down at the level of DNA. DNA is about 2.5 nanometers across, and this is the scale that we're manipulating matter and controlling it. In fact, it's not far off the atomic level, really, with a carbon atom being just a fraction of a nanometer. And as we alluded to at the start, it has kind of an interesting history, because it seems to be something that is everyday now. Nano is not an unfamiliar word in science circles and not in the media either. But we don't have to go back very long until we didn't have a word for it. So in 1959, Richard Feynman said there was plenty of room at the bottom. And what he was meaning by that is we're concentrating a lot of our activity on certain areas of science, but actually there's a whole level down below that molecular level that we could be understanding and using, something that we've not started investigating yet. And it wasn't until 1974 Ettore Cannucci coined the term nanotechnology. So until the 50s, we weren't thinking about it. Until the 70s, we didn't have a name for it. And so Taniguchi looked at ion ball milling, so he would kind of force things into incredibly small structures. So in the 70s, we got a name. In the 80s, IBM allowed us to start seeing down at that world, or imaging down at that world. So 50s, we thought about it. 70s, we named it, and in the 80s, we started being able to see it. If you can see something, then you can start to understand it a little bit better. Also, the 80s was an interesting time for nanotechnology. We had these fantastic innovations by IBM allowing us to visualize down at the nanoscale, but also we had the rise of popular science taking a hold of nanotechnology. In 1986, Engines of Creation, a book by Dr. Drexler, who did some work at MIT, came out, and that prophesied what nanotechnology was going to be. And it was good and it was bad. There were some really interesting ideas. Drexler imagined a world of nanoscale machines and gears and cogs, and effectively taking our current world technology and just shrinking it down. And that was a kind of a nice idea. The trouble with some of his predictions, the one I hate the most, is the grey goo prediction. Drexler was the one who came up with the idea of nanotechnology and self-replicating robots that could consume everything that you come in contact with. And that was something that was terrifying and exciting, and science fiction cottoned onto this idea, and it caught on, and we see it in lots of, there's Futurama episodes about it, you can see it in Star Trek. Any sci-fi franchise has elements of Drexler's doomsday scenarios in it. But they weren't really realistic. They caught the public imagination, but they're not realistic. A couple of years later, IBM started manipulating individual atoms. So here we have 35 xenon atoms arranged into the IBM logo. Super cool temperatures, and we're able to manipulate matter. So at the start of the 80s, we're able to see it. By the end of the 80s, we're able to move it. An odd trend in nanotechnology is to see something, create something, have the ability to do it, and then do novelty things with it. So IBM, some of you may have seen this, IBM created the smallest movie in the world in 2013, which was individual atoms positioned to make a small story of a person kicking a football. And it's an odd trend in nanotechnology. Discover something. We can see it, we can move it. Okay, what cute stuff can we do with it to get it on the front cover of Nature? And then we'll find an application for it a little down the line. Visualizing down at the nanoscales is incredibly important. I am a massive microscope geek, and I love everything to do with microscopes. And I just wanted to, I've got one here, not a microscope that we'll see is down at the nanoscale level, but just an optical microscope. And I'm going to put a live feed up. Is this all right? Yeah. Could I borrow anyone's phone for a second? I don't need it even unlocked. Anyone got a phone on them handy? Yes. Brilliant. I'm just going to stick this under the screen. So we're just going to have a little look at your phone. So I'll just keep it lit up. And do you know what kind of phone this is that you have? It's an iPhone. And I'm just going to make sure it's lit up. Okay. So while I see a nice bright screen with text and image on it, when we look at it under the microscope, we see a slightly different picture. So here we're seeing all the different pixels. Now, does anyone have another? So that was an Apple that doesn't have a make on it, maybe a 4 or 5-ish. Anyone a different that's not an Apple 4 or 5-ish? Let's go with that. I've never seen one of those. So, Apple XS, same make of phone. See the differences? Yeah, so then you'd agree that. So Apple are a really interesting one. You can chart the rise of their technology through looking at the pixels on their phones. Again, this isn't the nanoscale, but it is giving us a little insight into the tiny electronics that are in phones. I'll give that back to you. Thank you very much. And it's something I find quite interesting. So I took successive generations of iPhones. So this was an iPhone 4. You can see the pixels here. When Apple moved from iPhone 4 to iPhone 5, you can see that they halved the number, they halved the size of the pixels and doubled the number of them, increasing that resolution. As we move from 5 to 6, they adopted a slightly different shape with this kind of almost little arrow shape and break between them. Again, more pixels were included and slightly smaller. When we move from 6 to 7, an interesting thing happens. You might notice that actually 6 and 7 are the same. We're getting down to a resolution that our eyes wouldn't be able to detect any difference. So there's a limit to how small you really want to make the pixels. And so this, by 6 and 7, even through to the XS, they were a bit smaller, changed the layout of them, but giving us that better resolution. That's just over a few years. And that's as we're getting more sophisticated, making micro and nano electronics, we're able to shrink the technology and introduce more. Now, we wouldn't get very far with optical microscopes. We do need something smaller, and so when you're imaging down at the nanoscale, you're using electron microscopes. Effectively working the same way as optical microscopes do, but using magnets to focus a beam of electrons rather than using lenses to focus a beam of light. And things look a little bit differently. So here, a 5p piece under an optical microscope, you can see the kind of shine on it. It's silver. Through into an SEM, a scanning electron microscope, you see that it's now a grey. Electrons aren't able to see colour, so any image of nanotechnology that you see that has beautiful colours in it, they have been artificially added, because all electron microscopes produce grey images like this. We can zoom right in until we're getting to a level where it doesn't look familiar to our eyes, difficult to understand. And then if we switch on to a different type of microscope, so this is a transmitting electron microscope where the electrons are passed through the material. This is a piece of bismuth and iron. We're actually able to individually visualize columns of atoms. These are columns of atoms going through into the screen there, and we can even see where there's some dislocation, so you can understand what is going on between individual atoms. Imaging is part of the story. Imaging allows us to understand what is happening, control, and then build what we want. And when it comes to building nanotechnology, it's a challenge. Back at that football stage when I said you can pick it up, nanotechnology, you can't. Yes, IBM are able to nudge individual atoms around, but that will only get you so far if you want to build complex devices. And one of the biggest challenges is trying to work out, well, how do you take your atoms and how do you build something working and functional in the lab? And there's a few different ways that you can do that. I've got some wafers, if anyone's curious, you can see them later on, with nanoscale electrics printed on the surface of silicon wafers. And that's normally how we do things. There's a couple of ways that you can do it. One way is to cover all of the surface in the metal that you want. So let's say we cover this in nickel. And then you kind of scrape away the areas that you don't want, getting smaller and smaller until you're left with nanoscale structures on the top. The other way we can do it is we can put a sheet of plastic effectively over the silicon wafer and use an electron beam to write the pattern into the plastic that we need. We then can remove anywhere we've written with the electron beam and put our metal down, then wash the rest of the plastic off, leaving just small structures on the surface. And that gives us nanoscale structures in various ways. The other way of doing it, the way I tended to use, was create the correct conditions for something to build itself. So I used different gas flows, different reagents, and created a surface condition. So this little Lego piece is quite a good example. It has these dimples on the surface, and these dimples are able to grip on to the Lego bricks. So what I would do is try and engineer a surface that would allow something like this to grow itself. Rather than throw all the bricks down and cut some away, I tried to create this surface which would allow one brick to stick. The next brick would stick on top of that, and on top, to build more and more structures into the pattern that I want. So understanding surfaces is incredibly important. Now, why nanotechnology is important and interesting and different has a whole range of properties. Some of them are incredibly easy to understand. If you have an apple, and you cut it in two, let's say, the white inner surface will start to corrode. It will start to go brown. If you chop your apple into many, many more pieces, then it will start to go brown faster. The apple will decompose quickly because the oxygen is able to access the inner surface if we put in a split. So the smaller the material, then the higher the surface area and the faster the reaction will be. This becomes important when you consider some of the applications of nanotechnology. So one that I looked into was hydrogen storage. Now, hydrogen storage using hydrogen as a gas has been used before and proven not to be incredibly effective. Hydrogen fuel as a liquid is also currently used. So NASA sending rockets up, you have canisters of liquid hydrogen, an incredibly clean and energy-dense fuel, and that's a liquid. But my gran drives, and the idea of my gran driving that terrifies me. So we need a better solution. This is where the nanotechnology comes into play, the kind of hypothesizing of solid-state cars. Thinking back to that apple, all chopped up, with its inner surface exposed to the air. We do something very similar by having nanoscale sponges, effectively, for hydrogen, where almost all of the inner and outer surface is accessible to the gas, allowing you very quickly to put gas in, to absorb onto the surface, or to get gas back out. And it's potentially much safer than the liquid or the gas, and also more energy efficient. It takes quite a lot of pressure and temperature to store hydrogen as a liquid. So shrinking that down, having a high surface area, effectively a sponge for hydrogen. The area I worked in as well, related to space, was the Voyager space probes and what powers those. I worked on the device trying to improve the device that was sent up with Voyager. This little leg here is a thermoelectric generator. That is basically a red-hot plutonium rock with semiconductors strapped around the outside of it. The semiconductors absorb the heat from the plutonium, and they use that to power the onboard computer and Voyager. This was what my PhD was specifically in. If you crack those semiconductor devices open, you'll find lots of little cubes. Half of the cubes are N-type semiconductors and half are P-type. N-type, just to picture it, you can picture a material with too many electrons. P-type, you can think of it as a material missing electrons having positive holes. When these are connected up together and heated from underneath, electrons will diffuse away from the hot side. Positive holes will diffuse away from the hot side. Connecting these up means you can have a net negative flow. So whenever you have these devices keeping one side hot and one side cold, they will produce electricity. Hopefully, I can show you. Because I brought some with me. Some that you don't even need plutonium to use. So I've got some ice here, and I'm going to be the hot side, and I've got one of these devices. You might also recognize it as a Peltier cooler from the back of little fridges, but filled with these semiconductors, hopefully, with my hand as the hot side, and the ice as the cold side. Just thinking about it. Maybe nothing. Science though, isn't it, right? I'll try again. So what I'm going to do is, I'm going to spin the little wheel and you're going to go wild. Thank you. So I'm not telling you, it maybe just didn't survive the journey down. I'll have a look at that later. But these devices tend to be pretty reliable. Normally. Certainly working okay for the Voyager space probe, but we need to make them a little bit better. So at best, my body heat is really going to be able to power that little motor. Now that takes a lot less power than your iPhone. So if we want to make these better, then we need to start thinking about them in different ways. So what I was doing was, instead of using blocks of material, using nanowires or small materials, even crushing something and then pressing it back together can be advantageous. So if you think about, you want to keep one side hot and keep one side cold. Introducing lots of fractions and barriers can make heat kind of stay on this side. So it makes the thermal transfer a little bit trickier. And that's what I was doing by shrinking these down with nanoscale materials. If you think about a bus shelter, have you ever seen a bus shelter that has been smashed and you see all the kind of fractures in the glass? It's a little bit similar. As one block of material, heat transfers through very easily. As soon as we start introducing lots of little boundaries, it's a little bit harder, while the electrons can still pass through those boundaries. And the reason I was shrinking these down was so that we can take applications not just for Voyager space probe, but shrink them down. And so like here we have, this woman here has these devices in her wellies, absorbing her heat from her feet and using them to charge up her mobile phone, a kind of idealized example. Or here is me wearing some wearable thermoelectrics. So shrinking these down, able to wrap them around, uses wearable devices. Again, powering the electronics that we carry around with us. And I mentioned at the start that surfaces are incredibly important. Not just the design of surfaces, but the use of surfaces. And this is one of the biggest areas of nanotechnology. Surfaces can be made hydrophobic, repelling to water because of a nanostructure. Very often we take our inspiration from nature when looking at these. So a lotus leaf, water will roll off a lotus leaf, and it's because it has a very small and irregular structure on the surface. Water can't find the space, effectively, to spread out. We can look at this, we can understand why the water droplets stay as beads. We can then coat surfaces with structures that mimic the ones found in nature to make it water repelling. If you could then coat an entire ship with it, you could improve fuel efficiency by about 24% if the hull of the ship was hydrophobic, cutting through the water. Not only can we make surfaces smooth and repellent, we can also make them sticky. A kind of famous example of nanotechnology is Gecko Tape. Looking at geckos' feet, they have all these tiny bristles on the end of their feet, and that allows them to use van der Waals forces to stick to even smooth surfaces. Really related to that high surface area. And this was something that was shown in a kind of proof of concept where Gecko Tape was made, replicating these little pillars on a piece of tape, which was able to carry about 100 grams. So half a centimetre was able to hold about 100 grams. Not quite the gecko, as advanced as the gecko just yet, but they've tried using it on flexible substrates and they found that actually it's quite promising. They're even taking just the surface structure, so that's just a structural thing that's being used, and combining it with chemistry. So they're looking at how kind of muscles cling to things as well, incorporating the geckos and the muscles and working out how to improve a tape that doesn't require a chemical adhesive, it's just a structural property. Surfaces are important when it comes to stem cells as well, and this is one of the most interesting results, I think. What you see on the screen is two different experiments. There's a silicon surface and there are blobs. The blobs represent stem cells. This was Matt Dalby at the University of Glasgow. And what he looks at is how stem cells respond to different surfaces. And what he discovered was if you put stem cells on a surface which has regular holes in it, regular pits, the stem cells don't differentiate. They stay as undefined stem cells. He found that if instead you use a semi-regular array, the stem cells differentiate into bone cells, which is quite extraordinary. He also found if you used a random set of holes, just randomly spaced them, again they didn't differentiate. It only worked when it was semi-regular. There's a maximum distance that the holes need to, the holes can be spaced in. It's almost a kind of cat and mouse game. The holes almost kind of tease the stem cells into stretching out just to be kind of get to the next area, whereas on the regular rate it doesn't happen. So controlling surfaces can allow us to control cells as well. And this is being used, or hoped to be used, in things like implants. So anytime you want to control cell growth, then just by writing a pattern on a surface could encourage or discourage cells to grow in the way that you want them to. And there's an evolution that happens in nanotechnology as well. As we start off with our kind of embryonic understanding of nanotechnology, we eventually find its more powerful uses. An example of this would be titanium dioxide, that I'm sure many of you have come across. Titanium dioxide is what makes toothpaste white. It's one of the most used pigments that you'll find. So it's a white pigment, and it's been used as that for a long, long time. In papers and paints and any electrical goods, whatever you find that's white, chances are there's some titanium dioxide in it. So that's step one, using small particles to make something colourful. Step two in the evolution of titanium dioxide was its use in sunscreens. This is one of the first commercial applications of nanotechnology, using incredibly small particles of titanium dioxide to absorb harmful UV radiation. So that's pretty good. We're starting to get more sophisticated with our use. It's not just about making things a certain colour, we're actually using the properties of it for another purpose. But the evolution of titanium dioxide is not finished yet. What people are looking at now is taking small nanoscale particles and embedding it into either plastic or glass, absorbing the harmful rays from the sun, performing a photocatalytic reaction, and will attack anything that is trying to adhere to the surface of that. So using titanium dioxide, you could make self-cleaning windows, or in this case, the hope is that you could make water purification bottles, so that just by leaving bottles out in the sun, it would be able to kill some of the harmful bacteria in them. And so we evolve. We start off and we find new purposes and new ways of using the technology we've adapted. Not only are surfaces important, origami is important when it comes to nanotechnology. And giving commands to instruct DNA to fold up was a fantastic breakthrough. As I said, when you understand how to do something, so you discover you can fold DNA, what's the first thing you do with it? Novelty. You make a little face, and this was a front cover of Nature in 2006. When packets of DNA were able to link up to each other to form any structure that you could choose. So again, we learn how to do something, we start playing with it, and eventually we're getting to areas where we can use that more purposefully. So instead of making novelty structures, make structures which could potentially enter the body and be useful to us. Not only is nanotechnology useful, it's also beautiful. Simple examples, it isn't exactly technology because it's not control, but if you ever see oil spilled on a rainy day, you'll be seeing thin film interference. So getting different structures depending on the way the light is bouncing off the surface of the oil and off the surface of the water. We're getting a structural interference pattern. Something similar can be reproduced down at the nanoscale level. So the morpho blue butterfly does not contain any blue pigment, it's a structural coloration. The little kind of scales that the butterfly has have a nanoscale structure. The structure is comparable to the wavelengths of light that is hitting it. And because of that, you get this interference pattern again, and only blue light is reflected back to you. And that's something that can be reproduced, again, in the lab. So learning from nature and reproducing. So altering color perceptions with nanotechnology as well. It's one of its biggest applications, and one of the biggest irritations for me is this idea. Something that you might have seen in some newspapers or online. Nanotechnology as the submarine, as the robot, as the repair device that enters into our body. And maybe already you can see there's quite a big difference between me showing you surfaces where we've deposited nanotechnology through to this. And there is a big leap. If we think through the idea of it, it's a fantastic idea. If we to imagine that you were all cells in the human body. So we're all cells. And then if some were damaged, so we damage some of the cells. Let's say up in that back corner, there's something wrong with you. And that's a problem. Now, there's a few different ways that we could deal with that. So if I wanted to kill that section of the audience for being damaged cells, there's a few options. We could say to security, just close that off and kill all of you. We'll just kill everyone in the room and it will solve the problem. Ideal, but does a lot of collateral damage. Another option might be for me just to launch myself off the stage, fight my way to you, and bludgeon each one of you to death. Again, that would work. This part of the audience might be happy with that solution. But I would leave a path, a trail of destruction in my wake as I fought my way through, because I'm quite big. Instead, the idea of having something small and maneuverable, so like this drone here, becomes an ideal situation. This is something that is small, maneuverable. It has a camera on the front of it, and I can also control it. So I would be able to, if health and safety allowed, fly this over towards you using the camera to detect where you were and crash it into just you. And this is where our idealized version of nanotechnology comes from. The fantastic voyage, the submarine that can target just the area that we want it to, leaving everyone else intact. A wonderful idea for medicine. But this becomes a complex thing to build. This has a lot of parts in it. It has propellers, it has cameras, batteries, controllers. And so if I want to build something on the nanoscale that complex, I'm going to start having a problem. If you think of Lego again, if I ask you to build a little tower, that's quite easy. You can build it and it can be quite small. If I then said I don't want a tower, I want a wall, it's going to have to be a little bit bigger. I want that wall to be a house, it's going to have to be bigger. I want the house to have 4 rooms in it, it's going to have to get bigger. Every time we add a new feature onto our device, our material gets larger and larger and larger. And remember back to that definition at the start, we need to be below 100 nanometers. There's a fixed number of atoms, effectively, that we're working with, that we can go in any direction. So the idea of the fantastic voyage starts to fall down, because we can't build devices that complicated. But it doesn't mean that we can't do something amazing. It doesn't, just because we can't build a submarine, we can't build the needles in the hands, and this is the terrifying, this is Drexler's vision of nanotechnology, which doesn't and won't exist. Instead, it looks like something like this, like a cage of atoms. And we might be able to pack medicine inside that, have receptors around the outside so that it will target only damaged cells, and that's where we're currently experimenting with. Or I mentioned the DNA faces a moment ago. You can turn, instead of faces, you can create cages. So again, the idea is that medicine can be put inside these DNA cages, transported to the damaged area and delivered just to that target area. But for me, it's kind of like nanotechnology is a bit like Amazon Prime. When the Amazon Prime person comes to your door, they deliver your package. You don't also then invite them in to fix your sink and to hoover your carpet. The idea of introducing a submarine into the body that will cure your headache and then go ahead and fix your wrinkles isn't going to happen. We give these things one purpose. Maybe deliver this, take this, find this, move this particular direction. And that is where we're going with nanotechnology. We're not totally there yet, but we're getting more and more sophisticated. Again, it's the idea of evolution. We started in a world where we hadn't seen it, we hadn't named it, we then saw it, and we started working with it. And our first uses, things like titanium dioxide, that white pigment, is just a passive use. So we put little particles in and it just absorbs or does something. It sits. It's nice. It's functional. But it's passive. What we need to move to is an active area of nanotechnology. Something like Tickle Me Elmo that can react in a certain way. So it gets a signal in and it will respond to that signal. And maybe even one day we'll go past the active through into an area where we can have complex features, which, yes, are able to sense and react, and maybe react in slightly different ways. And that's where we are with nanotechnology just now. It continues to grow, and every week there are around 3 to 5 new applications hitting the market. And that's not going to change. We're going to continue growing the area of nanotechnology, growing our understanding, and also growing our understanding of the dangers. The dangers aren't like Drexler and the doomsday scenarios. And anytime you see those tiny little submarines, maybe point out that's not the best image to use. Nanotechnology is something that is beautiful, it is wonderful, and we continue to learn. As long as we continue to control, we'll be able to do it safely. And who knows where it might go in the future. Thank you very much. So we do have time for questions. I'm going to start, while we're working out questions, why this didn't work. I'm going to ask myself a question first.
I'm just going to step back while you do
Yeah.
that.
Sorry.
Does anybody in the audience have any questions they'd like to ask at this point? I'll wander over. Let me bring the microphone. You all right to do? Okay, thanks.
Hi, Jamie. Thanks for the talk.
Hello.
Quick question. Where do you see nanotechnology going the next 5 or 10 years? How will it change society and help us in everyday life?
Well, it's going to continue changing as the way it does. And our evolution of electronics is one of the biggest areas. It's always going to be an area that is going to slightly disappoint us for the next while anyway. And it's because it's still a new concept, and when we got to the 80s and we realized, oh my goodness, we can use this, our dreams exploded. But our dreams need to fit into reality now. So it will continue to affect us with improved devices, smarter phones, better laptops. We'll continue to explore medical applications. But because this is an area, you're talking about an area that is so small, it's smaller than a cell, and introducing that into the body comes with potential risk that we need to understand. So you're not going to see the world absolutely changed over the next few years. It will be small tweaks, because this needs to be a slow journey, and it's going to be 20, 30 more years before we're really using it for extraordinary applications. So little tweaks over the short term as we continue to learn so that we can introduce things in a safe way longer term.
Anybody else? Yep, go on. I'll bring you the microphone.
Thanks. What about integrating sort of like biological agents and nanotechnology, using viruses in combination for the body?
Yeah, so that's another way of doing something very similar. So I think, as an inorganic chemist, I think about creating structures that are able to do things. And despite the fact I constantly reference, nature has found this way of doing it, nature's found this way, it's an area I don't know much about. And I think they're almost kind of competing streams of who's going to get there first. Is it going to be the control of the biological, or is it going to be the absolute artificial? For me, the world that I work in is we learn from the artificial, we learn from the natural, and we recreate. The control of the existing natural is an area I don't understand. So combining them is a little scary as well. I'm not sure if that answers your question or not. A little. I see them as different strands just now. There may be overlap, but let's understand each strand first before we smash them together too much.
Anybody else? Going once. Oh, yep.
There's already the theory of the quantum dots in biological, so delivering medicines or targeting certain cells.
Yeah.
Do you think that this will be able to compete with that eventually one day?
So naturally occurring quantum dots. The natural occurrence isn't something I'm very familiar with, but quantum dots have kind of limitless potential. I kind of lump them into the same category as nanotechnology, even though some of them are even smaller. But the electrical applications are fantastic. The naturally occurring ones, I'm not familiar with that. I've got a question for you. Does anyone have a lighter? Yeah? This could work. This could work.
I'm staying out of it.
Don't we? Brilliant. Thank you. Can I enlist you to... Not going to hurt. It's totally safe.
Okay.
So just hold that. I'm so disappointed for you. I think I've broken the motor when I put it on. Because it worked earlier. Well, I've certainly not convinced you about the benefits of thermoelectrics anyway. Sorry. Thank you. I said we're working on them. We need to make them better.
Any final questions? No? Okay. Well, thank you everyone for attending this talk. The next one is at 12 o'clock, I believe. And a final round of applause, please, for Jamie Gallagher. Thank you.
Thank you.